Hello, this is Team 19's interim presentation. The members of this team are Danny, Adam, Will, Cliff, Anders, and Caden. We chose to analyze and redesign a kick scooter. Kick scooters are children's toys that can be used for transportation and playing. They are also sometimes used as extreme sports equipment in places like skate parks. Scooters have two wheels, the rear wheel is fixed and the front wheel turns to allow for steering. The scooter is made of mostly aluminum for its low relative density and reasonable durability. We estimate a production volume of 300,000 units per year. Our primary customers are toy distributors such as sporting goods stores, supermarkets, or department stores. Our secondary customers include recreational scooter riders, extreme athletes, and the parents and guardians of these users. Here is our CAD overview and parts list. You can see a comprehensive exploded view as well as a close-up of the wheel assembly. The entire assembly includes a deck, 2 tires, 2 wheels, 4 ball bearings, 2 axle spacers, a fork, 2 axle bolts, 2 axle nuts, a handlebar, 2 handlebar grips, 2 handlebar end caps, a clamp, and 2 clamp bolts.
Moving on, we will go into our product analysis. The fast diagram pictured here describes the function the scooter must perform. We have one main task function being to transport the rider. Branching from that, we have our primal basic function, roll on ground, and our 4 primary supporting functions.
For the first assembly procedure, we start with the deck as the base and install the rear wheel assembly, which consists of the wheel, 2 bearings, and a spacer. We then assemble the handlebar sub-assembly by attaching the grips and end caps and insert that into the deck. From there, we install the clamp and fork into the handlebar deck assembly. Finally, we repeat the rear wheel assembly procedure with the front wheel and insert that into the fork. In order to streamline the assembly procedure, the second method starts with the handlebar as the base. The grips and end caps are attached, and the deck is then attached to this handlebar assembly. The clamp and fork are then attached to the handlebar assembly. Finally, both wheels are assembled with bearings and spacers and inserted into the full assembly. By making these adjustments, we are able to improve the ease of assembly for our scooter, mostly by streamlining our parallel assembly and subsystem testing capabilities. While the ease of transfer and handling is slightly better in Sequence 1 with the deck as the base, being able to test the wheel and handlebar assemblies as well as being able to assemble both wheels simultaneously outweighs this drawback.
This table demonstrates our functional component mapping matrix where we match the parts of the scooter assembly to the leaves of the fast diagram, specifying which functions are performed by each component of the scooter. The most common function shared by different components is the roll on ground function. The number of components completing the same task should be reduced in order to increase the modularity. Here we have a bill of materials and cost calculations. We made the assumption that the manual labor rate is $18 per hour in order to calculate our assembly cost. Half of the parts on our bill of materials are purchased and the other half are manufactured in-house. The manufacturing processes used in order to create our parts are machining, welding, and injection molding. The total cost to produce one unit came out to be $57.37.
For our quad chart classification, we sorted the parts of our product based on their functional importance and their manufacturing and assembly cost. We can draw many conclusions from this chart, most importantly looking at the parts with high functional importance and high manufacturing and assembly cost. These parts, namely the deck, handlebar, fork, and clamp, will be some of the main parts considered for our redesign.
Moving on to product family design, we start with the functional differentiation table. Here you can see similarities and differences in functional use between our customer groups, which are differentiated between our end users, namely the recreational scooter riders and those who use scooters for tricks and sports. On the similar side, rolling on the ground, controlling direction of travel, comfort, and shock absorption are similar between target customers, while speed maintenance and stability differ between recreational and trick riding. Up next, we have the component compatibility table, which outlines the platforms and modules representing the components used in the functions outlined in the FTT shown before. On the left side, we have wheel, tire, spacers, axle bolt and nut, handlebars and their grips, clamps and clamp screw, which are the components that, no matter the customer base, will be used within the assembly. The modules include the bearings, the deck, and grind rails, which will differ in final product assembly for the target customers.
Here I will go over the variants of our design for our 2 customer groups. In this first original model, take note of the slots in the base as well as no pegs on the wheels. This changes once we get to our Scooter for Tricks, where we added grip tape for grip and control, removed the slots in the deck so the grip tape can be applied, and added bars for grinds and style on the wheels.
Here we show the product family assembly diagram. This first diagram is representative of assembly sequence 1 shown earlier, where the deck is the initial component for the final assembly build. Here you can see that both final scooter options have entirely unique assembly paths, which doesn't allow for any similarity between builds. This changes with the second diagram, representing assembly sequence 2, where the handlebars are the initial component in the build path. Here, the first 3 components can be assembled before the need for diverging into unique components when the deck is introduced.